Hi everyone, today we're talking about tools for detecting types of lung disease. After the 2019, the COVID-19 outbreak created huge challenges for healthcare. One of the biggest problems was diagnosing lung disease using X-ray scans. Hospitals were overwhelmed and doctors had to review hundreds of X-ray scans every day. This made their job extremely difficult, and many patients couldn't get timely treatment. Doctors work hard, but they're limited by time and energy. Checking X-ray scans is slow and requires great focus. This made us wonder how can we help doctors save time and work more efficiently. To solve this, we developed an AI statement to classify long X-ray scan images. This statement helps in three key ways. It reduces doctors' workload. It speeds up diagnosis. It supports areas with few doctors by improving efficiencies. This statement isn't just for COVID-19, it can also help with another lung disease. We believe technology like this can empower doctors, save time, and save lives.
So before training, I'd like to introduce our data preparation and data pre-processing method. Our dataset includes over 21,000 long X-ray scan images collected from multiple Kaggle sources. We categorize into five distinct groups to train our deep learning model, and we can see the sample size for each groups are imbalanced. As for the data pre-processing part, firstly, we resize all the images to 255 by 255 pixels, which ensuring uniform input dimensions across the dataset. Secondly, we convert RGB images to gray, which is focusing on structure patterns in the LUMs and reducing computational complexity. Thirdly, the dataset shows significant class imbalance, with normal lung images dominating. Then we applied data augmentation techniques through flipping and rotating to address balance. Then we normalized the pixel values to range of 0 to 1 and transfer to PyTorch tensors. Finally, we standardized the tensors by using ImageNet mean and standard deviation to align our data with pre-trained model.
Here is an overview of our model architecture. For this project, we chose ResNet 50 as the backbone. It's a powerful deep learning model pre-trained on ImageNet, which gave us a strong starting point with well-learned feature representations. We fine-tuned all the parameters to better adapt the model to our specific task of classifying long X-ray images. The input to the model is grayscale images, and we adjusted the final layer for multicast classification to align with our dataset's requirements. This approach combines a reliable architecture with fine-tuning, enabling the model to identify subtle features in medical X-ray and make accurate predictions. Overall, ResNet 50's designs helps it handle complex visual patterns effectively, making it a great choice for analyzing medical X-ray images in this project.
Now I'm going to talk about how the data is handled throughout the whole pipeline. The raw data provided in the zip file will be first extracted to a designated directory for processing. Once extracted, the data will be split into train, validation, and test datasets. Before augmentations, the training and the validation datasets will be standardized into 256 by 256 pixel grayscale images. This dataset then will undergo data augmentations and be converted into tensors. Both baseline models and advanced models will be trained using the training tensors, with performance validation conducted using the validation tensors. The parameter of both models will be saved as path file for future use. Finally, the test set data will then be used on evaluated on the models to assess their overall performance. The final output will be the trained models, along with the prediction of the testset data. Finally, to sum things up, we have separated the whole process into four parts to build our pipelines. Following these steps, we have created a front end to access all necessary steps to train a lung disease classification model as our final outcome of this project. Please watch the following quick demo. This is a quick demo of our web page. We have created a very simple UI for users to access without experience working with model training, and it contains 4 pages. However, due to the time limit, we will only show the last page, which is the inference page. Right now, I'm going to upload a image that is excluded in our dataset and I'll choose this model. This is the image that I have just uploaded, and down here are the results of the model evaluation of this image. As you can see, it's been correctly labeled as COVID-19 with 81% of a probability. We will have to show more details about this webpage. However, due to time limits, this will be the end of our demo. Moving on to conclusion. As for conclusion, we think deep learning classification model shows a high potential for detecting lung disease, providing doctors a more efficient way to diagnose patients. However, there are limitations of this approach. First, dataset bias may affect the generalization. Also, insufficient samples for some classes may lead the model to make predictions towards classes with more training data. For future improvements, we think integrating our current model with multimodal data will significantly improve the performance of the model, as well as train the models on a larger dataset. And that is the end of our presentation. Thank you.